Welcome to the second part of the afternoon program. I'm Dennis from Skyline. Welcome here in Skyline Park on behalf of myself and some of my colleagues that you see in the audience. Skyline, right? Who are we? Well, you already met Frederik in the beginning. He's our CFO, Frederik van den Bergen, and he's leading this company together with his two brothers, Ben and Bert, right? So Skyline is really a family company. It was founded in the 1980s by Leo van den Bergen as a hardware company, and then his three sons took over and they turned it into a software company. Here are some key facts and figures about us. I'm not going to go through all of these, but yeah, we have over 1,500 customers currently in over 125 countries worldwide. We have more than 350 people working with us, but our main office is that one right there, where we're at right now in Isegem. We have about 200 people here, and all the research is done in Isegem. All the core development, it's all done in Isegem. Here is a list of a few of our customers, and you will probably recognize a few of them already. Disney is a big name, and you have HBO and AT&T, for example, in the States. But then closer to home, you have British Telecom, BT, you have Sky and Deutsche Telekom. And then here in Belgium, you have Telenet, Proximus, VOO, and so forth. So as you see, our customers are telecom operators. Now, why do they want to use our product, right? Well, a telecom operator typically has a lot of devices he has to keep track of, right? And you can think of an example, for example, Proximus. Well, if you're a customer of Proximus, you have a device at your home, like a modem. Well, that's part of the Proximus network, right? But then there's more to it. Proximus, Telenet. Telenet, for example, has an amplifier in every street. So there's also a whole bunch of amplifiers that these operators need to keep track of. And then you have encoders and decoders, and then you have servers. And so you have a lot of devices that these telecom operators have to monitor. And that's where we come in, right? So we create a piece of software called Data Miner. And I'm going to start by showing you a little bit what it looks like, right? So let me go out of the presentation. And let me show you, are you not seeing this yet? Voila. And let me show you a little bit what this looks like, okay? So this is our main UI, basically. And on the left-hand side, you see a list of basically the devices that the customer is using. So for example, in this case, imagine your Telenet, you arrive at work, you open up the screen, and on the left-hand side, you see all of your devices. You have some devices in Africa and Australia and Europe. And then in Europe, you have some devices in all kinds of cities, maybe in Brussels. And then if you want to have some information about the device, you just click on it. And what happens is this opens up the device in Data Miner. It's like a digital twin. And here you see how the device is doing right now, right? For example, this server currently has a total processor load of 67%. The available physical memory of the server is at 52.8 gigs, and so forth. Right? Now that's the current status of the device, but you can also go back in time. Say you want to analyze a problem that happened in the past. Well, you can simply click here to open up a trend graph. And now what Data Miner is going to do, it's going to try to fetch the historical data of this parameter, and it's going to display this on a trend graph. It's taking a little bit of time now, just to show you that it's all real-time demo. Voila. So here's the data, and it goes back a year in time. You can get historical data. Another thing you can do in Data Miner is ask the system to monitor certain parameters for you. For example, you can tell the system, look, Data Miner, if my total processor load ever goes above 50, well, could you trigger a warning alarm? And if it goes above 80, could you maybe trigger a major alarm? If it goes above 90, can you maybe trigger a critical alarm? And all of these alarms, they appear here at the bottom of your screen in what we call the alarm console. Okay, so that is in a nutshell the main UI. The device is here, information about the device, you can communicate with the device, and the alarms that are triggered. Right. Okay, so let me go back to my presentation. So how did these people come in? We really used the same slide this morning. This is us. You see some of these people sitting in the audience. So where do we come in? Well, you have all of these devices that we're monitoring, right? Millions of devices described by millions of parameters in total. And we want to analyze all of that data in real time for two main reasons. First of all, proactive monitoring. The idea here is that we try to predict issues before they occur. And for that, it's very important that we have a good anomaly detection algorithm. So you see immediately the link with Conscious. If you can detect a small behavioral change, often that's an early warning sign that something is about to go wrong. So it's very, very important to detect these subtle changes. So that's your anomaly detection component. If we're not able to predict the issue, say an issue happens, then the second thing we try to do is we're going to try to help the operator to solve the issue as fast as we can. And that's the reactive assistance component, right? How does this work in a networked environment? Well, in a networked environment, all devices are connected to each other, right? So if an issue happens on device A, it propagates throughout the network. So if we want to help the user to find the root cause, we need to know which devices are related to each other, which parameters interact with each other. So that's where this contextual component of the Conscious project comes in, right? We want to learn relations between the components in our network. Here you see an overview of the work that we've been doing during Conscious. So we've been tackling a lot of different things. I'm not going to go through all of these, but the main thing I want to emphasize here is that first we had a lot of very nice collaborations with the KULeuven, with Sirris, with the University of Antwerp. And here, we met a lot of great people. We had a lot of great insights, a lot of very nice collaborations. So just because of that, this project was already a success for us. Second, also, what I would like to emphasize is that out of these 10 items, 5 items resulted in concrete features that are already implemented in our software. And they're currently being used by customers all around the world. So also from an economical aspect, the Conscious project has been a great success for us. Right. So thank you for your collaboration, partners, and employer. Now, what I'm going to do in the remainder of this talk, I'm going to go over the features that we did. I'm not going to go into too much detail, but I'm going to show you some demos of how the features that we have already implemented, how they work. And I'm also going to explain a little bit how all of the work we did links with the university partners. Okay, so let's dive in. The first thing I want to talk about is relation learning, learning context, right? Learning the relations between devices and between parameters. Here, we started by using a very simple idea. Assume that you have 2 parameters, say the CPU load and the memory usage, right? And assume that they always have alarms simultaneously at the same point in time. Well, it's likely that those parameters are related, right? Okay. That's a very simple idea, but to apply this in the real world is a lot more difficult. Yeah. First of all, what does it mean for alarms to co-occur? In reality, think about, say, Telenet. They poll their important devices every 10 seconds, but the cable modem you have at home is only polled every 15 minutes or so. So you're not quite sure when a device went into alarm. Sometimes there's a big delay. Right? Also, alarms are unreliable. Now remember, when is an alarm triggered? Well, it's a user that's saying, oh, if this goes above 80, there's an alarm. But sometimes the value is just above 80 and sometimes it's just below 80. Right? So sometimes there is an alarm, sometimes there's no alarm. Also, the amount of relations you have to learn. Right? If you're monitoring millions and millions of parameters, then how many pairwise relations do you have to learn? Well, that's like millions and millions squared, basically, right? So this scales quadratically. And to create an algorithm that's lightweight enough, fast enough to do that is a very big challenge. And finally then, what about relations that change over time? So if a user has 2 devices, A and B connected, and then he unplugs a cable, and he connects device A with device C, our algorithm should be able to pick up on that after some time. So there were a lot of challenges here that we had to overcome, but we were able to create a relation learning algorithm and add it to DataMiner. Now, how is this algorithm leveraged? right? How do we use it? How do we translate it to a concrete feature? Well, we did that in two ways. First of all, we now have a way to automatically group alarms together if they have the same root cause. We call that incident tracking. And I'm going to demonstrate it in a minute. The second way we leverage this is by helping operators solve problems by proposing them other parameters to look at. Say he's looking at a parameter A, then we're going to tell the operator, hey, maybe check out parameter B. We think it's related. I'm going to show you a quick demo of how we did this. So let me switch back to the data miner view. Voila, here it is. Voila, and let me go to this view. Okay, what do we see here? Well, don't worry too much about the details, but imagine you're Proximus, for example, and you want to broadcast a soccer game. And to broadcast that soccer game, you need several of your devices to work together. In this case, 5 devices. Okay, it's only 5 in this case. In reality, it will be more, but let's take a load balancer, 2 servers, and 2 web apps. Right. Now, I'm going to show you how these devices behaved in the past. So I'm going to go to the report section. And here at the bottom, you see those 5 devices again. And there's a heat map next to this. Now, what does that represent? Well, whenever it's green, it means that the device was behaving nicely. Whenever it's red, it means the device was in alarm. You clearly see it's a demo, but you see that whenever one device was in alarm, the other devices were also in alarm. So you clearly see the alarms on those devices, they always coincide it. So data miners should now be clever enough to group alarms together if they co-occur. What do I mean? If these 5 devices go into alarm again, data miners should be able to take those 5 alarms, group them, and show them as one to the user, right? Well, let's see if data miner can do that. So I'm going to go to my visual again, and I'm going to create this hidden button here, alarm. Now what that's going to do is it's going to create alarms on these 5 devices. And you see they're going into alarm one by one. There you go. Now these alarms have now appeared somewhere in this active alarms list. All right, so let me make it a bit nicer. So we can focus on the alarms that matter here. Voilà. Here they are. So let's see now if data miner can group them, right? I'm going to activate the feature that we created during the Conscious project. And voila, you indeed see data miner learned from the past behavior that such alarms, when they occur, that they should actually be grouped together. And this is of tremendous value to our customers because at the moment here, you see that we have 589 active alarms. On real systems, you can have thousands of active alarms at the same time. So if something happens, alarms just keep coming in, and the user doesn't know what is related to what, right? So this is a very valuable feature for our users. Okay, let me clean this up. And let me quickly show you another application of the relation learning. Right. This time, I'm going to focus on a trend graph. See if I can make it a bit smaller. Yeah. It doesn't really matter what you're looking at, but this is the signal level of a receiver. And I want you to imagine again that you're working at Telenet or Proximus, and you're looking at this and you're like, something is wrong. Can you help me out, data miner? Can you tell me what other parameters I can look at? Now in this case, alarming is not configured. The user didn't do the effort of configuring any alarm template, so we cannot use the alarms. But in one of the first projects we did with Flyo, we constructed an anomaly detection algorithm. And this monitors all your trended parameters, thousands and thousands and thousands, in real time behind the scenes. And you see this algorithm in action in a very subtle way, actually, because at the bottom you have these little gray cubes. They indicate that data miner detected change points, behavioral changes here. Now, when two parameters have alarms at the same time, they're probably related. But when 2 parameters change their behavior at the same time, they're probably also related, right? So the thing we did for alarms, we can also apply it starting from change points. It's not as simple as it sounds, of course. There were a lot of challenges. You have to look at how severe the change point is. Sometimes the change point is detected and sometimes it's just not detected, stuff like this. But let's see if data miner is now able to propose us, the telenet operator, if it can propose us to look at another parameter. I'm going to click this light bulb. And here data miner is saying, hey, operator, I noticed that you're looking at this. Maybe why don't you look at the forward power of the HPA2 device? Okay, I click on that. Data miner is fetching the trend data of this parameter. Now let me make this image a little bit nicer. Let's add a second y-axis, like so. Trying to drag it, like so, voila. And now you see indeed that it makes sense that data miner is proposing you to look at this parameter, because you see every time the blue one goes down, the yellow one goes up, right? Okay, let me quickly go back to my slides now. The demo I gave, voila. Okay, so those are already two features that we were able to introduce because of this project. But notice that the features have one Achilles heel, right? You cannot learn a relation if nothing went wrong before, right? You need to have seen alarms in the past, and then you can use them to learn a relation. Or you need to have seen some behavioral changes in the past, and then you can use that to learn relation. But what about the case where you didn't see anything bad happening before, right? That's why we decided to focus as well on generalized inter and intra-element relations. And here we had a very nice collaboration with Sirris and the University of Antwerp. Now let me tell you what I mean. So the cool thing about the customers that we work with is that they use a lot of devices of the same type. So think about Proximus or Telenet, the cable modems or the modems you have at home. They don't have one modem, but they have millions of modems that they're tracking. They don't have one amplifier. No, they have an amplifier on every street, right? So they have thousands of amplifiers. And they don't have one server, but they have loads of servers. So what does that mean? Well, assume that a fictitious company has 9,000 servers. Every image is 1,000 servers. And assume that the algorithm I just described is able to learn the relation that CPU load and memory usage are related on 8,000 of those 9,000 servers. Okay. Well, it makes sense that that relation then also holds on the other 1,000 servers, right? There are 9,000 devices of the same type, and you see a relation on 8,000 of the 9,000, and you don't know about the other 1,000 devices, then probably the relation holds there as well. That's the idea behind intra-element relations, generalized intra-element relations. During this project, we created a prototype to detect such generalized intra-element relations. And this was a big success. We validated the results with customers using customer data, and we reached a precision of 90%. We're very happy about that. We did score lower on recall than the Sirris method, but we were very happy about this result. Now, that's intra-element. You can go a step further now. Instead of looking for relations between parameters in a given device type, you can also look for relations between device types. For example, if a signal is flowing through your network and it's encoded somewhere, then it also needs to be decoded somewhere, right? So an encoder is always related to some decoder at some point. An amplifier is always related to many cable modems, namely the cable modems in that street, right? These are inter-element relations, and we also created a prototype to detect such relations. But here we were not able to finish, so we still need to do some further research to improve on this. Now, working on these generalized intra and inter-element relations, we didn't do that alone. We had some very nice discussions, some very nice conversations with really clever people, such as the people from Sirris and the people from Antwerp. So I'm very happy to give the floor now to Sirris, where they will talk about their work on intra-element relations. Here you are.
Get that in there.
Okay, thank you, Dennis, for nicely introduce our use case.
So indeed, we went researching on the event data of the alarms we received from Skyline. So we had a lot of data, really a lot of data. You have to see it as simple event data. So we have a timestamp, an alarm, and a device. And there we had to find relations within those alarms. But indeed, it has to be efficient. The computation should go fast with a lot of data. And we saw that a lot of parameter namings were also, or there's also a lot of information into the context of the device itself and within that parameter name. So if we look at the lowest level of detail, you have information in a parameter name of the device itself and the type of alarm. And we focused first on one device to find relations in there for each device, and then we do a step of generalize those alarms. So we also can introduce new devices that we also see the same type of relations there. What did we do then on one device? That event data is taken into account. If you zoom in one part, you see in 6 minutes we have 3 times the same group of alarms that is triggered. So there are certainly relations to be detected. What we have done in such a case, so on the element itself, on the device itself, you build a graph, and a graph with nodes, so the connection dots are parameters, and the links between the parameters are done, it's called a weight, and it's calculated by how many times it's co-occurring with another alarm, with some window to consider. Those weights in that graph can be seen as a chance of going from one parameter to another one. And in that perspective, we could use a Markov clustering. And a Markov clustering is a very simple set, taking those chances and going a lot of steps after each other to see if we go from one parameter to the other, what are the chances. And then we can assume that staying within a group of parameters, within a community, chances are higher you would stay in that community, and the chances are lower that you will switch to a community. And then that is the background of that Markov clustering, where if you do a lot of steps, the communities will appear automatically. And then the next step we had to take was to the relations we learned on the lowest level, to generalize that over all the elements, and to see what if we can find information over there. What we've done is text mining on those parameter names. So we found more common parts over the devices and combined the lowest level relations with the generalized parameters, and again do a Markov clustering to find generalized inter-element relations. The weak spot in that methodology is that text mining, because it's depending on your naming conventions, it's depending on the parameters of your text mining procedure to make sure you get out the most useful information and the most useful links. So here it's also useful to introduce domain expertise in this. And we can do this with constraint clustering. What is constraint clustering? You can see it as very simply as a task that you give to the computer. You have here 8 objects, cluster them. The computer will first say, let's put all the triangles together and all the squares, and you have 2 nice clusters, in his opinion. But the domain expert says, yeah, okay, I see where it comes from, but I want to see all the blue figures together. So you give to the algorithm a must link. You say, this one really has to be put together, recalculate. And then you find the groups where a domain expert is more likely to work with. It's more useful for the end user. We did that. Also, we did some tests on the Skyline data. And here you can see the output of that Markov clustering on one device. The left one is without a must link. If we do the Markov clustering, we have 6 clusters. But as you can see, here, parameter 3, 6, 7, 8, 9, and 10 are all clusters in one big cluster, and the rest of the clusters is very small. So you have the rest of the clusters are mainly 1 or 2 parameters. If the domain expert says, yeah, but parameter 5 and 6, they aren't, maybe not, in my opinion, they should be clustered together. Then the constraint Markov clustering is giving us 4 clusters, 2 main clusters where you have 2 equally sized or around equally sized clusters, and again 2 smaller ones. So we believe that introducing that kind of knowledge, you could improve the clustering for the end user, and he will have a more natural grouping or relations found within the team. Yeah, and then I give the word to Mom.
So, hi, I'm Len from the Fairmans from the University of Antwerp. I work at REM Data Lab. So we're in the Department of Computer Science, the AI and Machine Learning Lab. Also, some bioinformaticians that are part of our lab. Anyway, my focus is on novel algorithms for data mining, time series, and more specifically, motive and pattern discovery, anomaly detection, and classification. So for the Skyline, basically we have a context-aware anomaly detection problem. Like discussed before by Dennis and Annelies, for some customers like the broadcasting data set, we have hundreds of devices. There are, in this case, 5 different types of devices. And for each device, you have multiple sensors actually between 2 and 20 or something. And each sensor, then we have all the data collected over 1 year, and that be a sample every 5 minutes. And so when you want to detect anomalies on such a data set, there are 2 main problems. The first problem is we don't know which devices are connected. So that was the discussion we had before with the intra-device and inter-device links. And the second problem is, I assume you know the connections, when is the device behaving anomalous. So those are 2 interesting problems, I think. Also interesting from an academic point of view, because it's a huge amount of data, gigabytes of data. So any algorithm should be scalable. So that's a challenge. And typically also not studied by other researchers, because we don't have such data sets to our to use. So here on the right, you see an example of the output, and I put a link to a paper that's in progress of submission. So here we actually have every node is a device. We show the links between different devices. The colors of the nodes represent the cluster, and the shape can be triangles or circles, represents the type. Already talked about this approach. So what's the difference? So Skyline and Sirris mainly look at the alarm data, and Skyline discovers alarm groups, and a series with a higher recall or higher precision, I forgot, using Markov clustering. And so what we propose is to use the sensor time series, and we use time series similarity search. So the advantage of doing that is we have complementary outputs. Sometimes there's no alarm data available, and there's only sensor data, or the other way around. So that's nice. There's also actually a different focus. With alarm data, you're looking at co-occurrences of alarms, while I look at the general trend of the time series captures over a year. And it's also applicable on both intra-element relations, so within one device, but also between devices, which is the more challenging part, because there are hundreds of devices and I think 10,000 time series in this data set. So that's more computationally a harder problem. Okay, so for the first question, which devices are connected, what we propose is to just search for the most similar time series. And so here are two examples of that. So you have 10,000 of sensors, and we look just for the most similar sensor. And here you see the results of two different similarity measures. So the top one is using a piecewise aggregate approximation. Doesn't matter the details, but you see it finds a similar sensor within the same device, by the way, of transmitted and received bit rates. And then we have another example with the distance-based fingerprint, which is something I invented, which works good for bitrate data, and it finds another similar time series. And I think these two matches more clearly, and that's because with the distance-based fingerprinting, you count with the peaks more. So that's the difference. So what we did was a study of different similarity measures, classical ones like Euclidean distance and Pearson colorations, and other measures of similarity, and also implemented efficient algorithms for computing similarity. And so here we have 10,000 time series. It's cubic in that, so that means 100 million pairs of time series you have to compare, and we do that in minutes. And yeah, in this case, it's not like super smart algorithms. They're relatively simple. They're based on sampling. So instead of considering the whole time series, we take a small sample, compressed representation. And so, yeah, again, like you're taking a histogram or a fingerprint that's smaller in size, and then you can do the 100 million comparisons fairly quickly. And top-end retrieval, because since we're not interested in returning all 10,000 similar time series, but just the top few most similar ones. So that's one part. So as discussed before by Dennis, we can do that for a certain instance, for a certain device, and show similar sensor values. But there's indeed a problem of gaining knowledge. If we have knowledge about for this type of device, often CPU and memory are correlated, then that can be used for other customers who have the same type of devices. So what we do after the similarity search, we try to discover rules or patterns in that similarity matrix. So why? To gain knowledge based on the type of sensor, because we assume that if a new device is added for monitoring, it will conform to similar rules than other devices of the same type, and also to eliminate false positives in time series similarity search. Because when we're searching for something similar in a large database, you will always find something that is similar, maybe not what we want. And so here's an example of the output. So these are some rules for a first device type in that data set. And so for instance, the first rules tells us that for that type of device, you often have multiple capacity sensors, like the remaining space on a hard drive, and that these sensors are correlated, because for 100% of these sensors, we find a perfect match. We find a top one similar time series of the time capacity, which is the same. And that occurs between the device. So it's maybe a trivial rule, but it's discovered automatically. So that's interesting. Also here in the last column, you see the intra score is 0 for the third and fourth rule. So this means these are rules that occur between devices. So this rule states that if you have a sensor for the CPU system time, then in 70% of the case, we find another sensor which is highly similar to that one. And in this case, in another device. So that's still something we're looking at. If these rules are always true or semantically indeed similar. So that's still a little bit future work that we're pursuing now. Okay, that was the first part. Now the second part is on pattern-based discovery in time series. So the idea is to find frequent occurring shapes in time series and use them as features. So here's an example. For instance, we have here 3 time series, and this kind of shape we discover in both the first and the second time series. So we can go from raw values to another representation where at every window we just detect one or more frequent occurring shapes. And this is interesting. It's interesting for me because I like to study efficient algorithms, and this is a good setting. But it also is interesting towards application because turns out you can segment time series into using patterns, and that will be work presented by Louis from the KULeuven. You can also use it for anomaly detection in multivariate devices, and that's what I did for the Skyline dataset, and also some other areas where we have done work in the past. So here's a little overview from the paper. So here we start with 3 time series in one device. We usually, as a first step, discretize the time series, and then we don't have to deal with continuous values, but we can deal with letters. And here an A means a low value, and a D means a high value. And then we can search for patterns or strings if you want, like ADA means low, high, high, low, and with those patterns we match them then again in the original time frame, and in this case you would find that the third window is kind of anomalous because few frequent patterns occur, which is what we would conclude visually also. Okay, so for going back to Skyline, we do pattern-based anomaly detection in multivariate time series. So what is the context here? The context is a device has multiple sensors. Some of these sensors are similar within the device. Some of these sensors are maybe similar to other sensors in other devices. And of course, there's time. For pattern-based anomaly detection, we discover patterns, frequent occurring shapes in each sensor. Then a sensor is anomalous if few frequent patterns occur, so it's the opposite. If few frequent patterns occur, we consider it anomalous. We aggregate the results from multiple sensors together, and finally, by using patterns, we are also able to explain the anomaly score, which is not unimportant. And so here's a visualization of that. In this case, it's on a benchmark dataset because for Skyline, we don't have ground truth labels. So that's harder to validate this approach. So we validate it on other datasets that are publicly available. But what we see here are 4 different sensors. And for each sensor, we have the ground truth, which are the red squares. So these are known anomalies in each sensor. And then on the second, below the 4 time series, we have the anomaly score, which is between 0 and 1, the pattern-based anomaly score. And if it's close to 0, that means there's no anomaly. And if it's higher, close to 1, there's a higher likelihood of having a predicted anomaly. And in this case, we see a high correlation between the predicted anomaly scores in each sensor and the ground truth. And we would maybe conclude that this window, in this case, all 4 sensors, indicates that there's something unusual. Okay, yeah, that's it.
Hello. All right. Thanks a lot for the explanations, Annelies and Len, and very nice. The next thing I want to talk about is another form of relation learning, which is the time-scoped relation learning. Now, we're running a little bit short on time, so I'm going to skip the demos and just show some pictures to show you. Yeah? So what's time-scoped relation learning? Well, remember, we learned relations between parameters, right? But sometimes the same parameters are not always related, right? Imagine, for example, that you're broadcasting a soccer game. Maybe sometimes the signal flows from device A to device B to device C. And then another day, maybe the signal flows from device A to device K to device C, right? So sometimes a user can help the system if he tells the system what time range he's interested in. So there was a problem, and it could be nice if the user tells us, okay, in what time range are you interested? And that's what time-scoped relation learning is about. Now, without going into too much details, let me just show you what it looks like in Data Miner. So in Data Miner, imagine that you have a trend graph. In this case, it's the available physical memory of a server. But you notice some strange behavior. You notice that the available memory drops and goes back up here. Here, there's a more permanent drop. And then here, this is actually really bad, because here it seems that at some point, the available physical memory of the server started going down, and it's actually going towards 0. So maybe some process has started leaking memory. Now, as an operator, what you want to know? You want to know which process was responsible for this, right? And the naive approach to do that is to go through all your list of processes and opening the trend graphs and then seeing if there was some weird behavior. But now we've added the option for users to select a time range. So you can select the time range, and then you can ask Data Miner, look, Data Miner, in this time range, I'm interested in that. Can you maybe point me to some parameters that are related to this problem? So we click on the light bulb. And then Data Miner is saying, yeah, maybe why don't you look at the memory usage of your stock controller? Okay, you click on that. And then you see indeed that that process is the process that started leaking. Okay, so this is just a very simple example. But the people that are using it, they like this kind of feature a lot. It is very valuable and can save a lot of time. Okay. So I'm going to skip the demo. Just going to mention quickly one other thing that we did, which is that we added the human in the loop. So what's that about? Well, I already told you we have an anomaly detection algorithm, but it actually consists of 2 steps. First, we detect behavioral changes. And then as a second step, we're going to try to guess or estimate if this change that happened, if we should tell the operator about it, if it's interesting or not, right? For example, a noise parameter, if the noise, say there is an issue, the user solved the problem, the noise goes to 0. Well, our anomaly detection is, the algorithm is going to say, whoa, a big drop in noise, that's an anomaly. But it's not an anomaly that the user cares about, because it's good that the noise drops, right? So that's why we've added these thumbs up, thumbs down. And the idea here is that the user can tell the system, look, I don't care about drops in noise. You shouldn't tell me about this, right? And when you do that, this changes the internal state of our algorithm so that it automatically learns that for this kind of parameter, it shouldn't trigger this kind of event. And the future goal is to add this information to the cloud. Currently, a lot of our customers are connecting to the cloud. And if we see several customers telling us that drops in noise are not important, then we can start using that information for other users as well. Right. To end my part of the presentation, I want to explain the link of some of the work we did with the KULeuven. First of all, we also focused on multivariate anomaly detection in this project. Here, the idea is that our relation learning algorithms learn relations between parameters, but then we want an algorithm that learns the kind of relation. So for example, say that our algorithms say that the fan speed and the temperature are related. Then we want an algorithm that learns, okay, how are they related? Well, if the temperature goes up, then the fan speed goes up. And then we want that the algorithm tells us when that relation breaks. Okay, and Dan will talk more about that. So we're very thankful for that nice collaboration. Looking forward to having that in our software somehow. And then the final thing I want to talk about is our discord discovery algorithm. So for those of you who are unaware of what a discord is, imagine that you have a time series and you're looking at the last 10 points or something. And you're wondering if this is weird behavior. Now what you do is you take those 10 points and you compare it to every subpart of your time series. And if your 10 points lie far away from all those subparts, well, then that's weird behavior, right? We call that a discord. Now, if you want to do discord discovery, the bad thing is you need to have your data in memory. Say that you have your last 10 observations. You want to compare it to all the parts of your time series. So you need your time series in memory. But when you're dealing with millions of parameters, you cannot do that. You also cannot constantly fetch that trend data from the database. Because, I mean, yeah, that's too many requests for any database system to handle. So instead, what we did was we tried to find automatically representative parts of a time series, so that we don't have to store the entire time series in memory, but only the representative parts. And then when your last 10 observations come in, you just compare them to the representative parts. And if they're close to one of those, well, then there's no anomaly. If they're far from those, well, then you will still need to fetch the data and see if it's an anomaly, and you might need to update your set of representative time series. Now this links directly to the work of the KULeuven as well, because they're also looking for different kinds of behavior in the data. So I'm gladly to give the word now to the KULeuven, because they will explain it better than me, and I think, yeah, Dan, all right, I'm gonna give you. Yeah, and this is all I was gonna say, so just quickly want to say thank you to the partners again, really nice collaboration, and to Vlaio as well. Dylan? Okay, sorry about that. So I'm Dan, I'm from the KULeuven, I'm a PhD student. And before I kind of explain what I did within the Conscious project, I will briefly introduce our research group. So it's called DTAI, which stands for Declarative Languages and Artificial Intelligence. And we do research on a variety of topics. So we split these topics into two, let's say, pillars. So we have the fundamental, more theoretical research, like predictive learning and clustering, neurosymbolic AI, and functional programming, for example, just to name a few. But we also have this other pillar which focuses on applied research. And some of them are, so one of them is sports analytics, which may be very relevant today because of the European Championship. But maybe a little more relevant today is anomaly detection, as we're talking about the Conscious project. So 5 people were involved from DTI in the Conscious project.
two professors, Hendrik Bokeel from the campus Everlee and Matthias Verbeke from campus Bruges. One research manager, Wanne Smeert, and then two PhD researchers, myself and Louis. And so within the Conscious project, the KULeuven focused on the detection of temporal contexts. So Dennis has very nicely demonstrated the data miner tool, which kind of monitors a lot of equipment. And so monitoring this equipment over time results in time series data. And our goal is to detect time segments with same semantic meaning in this time series data. And then the second thing we focused on was anomaly detection. So detecting anomalies based on the identified temporal context. And so for context discovery, we've I focused on motive discovery, which is the task of finding patterns within a time series. It has briefly been introduced before by Annelies in the example about the fridge opening, but this has many other applications. For example, in the healthcare, the plot I show here is an ECG, so it measures the electrical activity of the heart. So there it's also useful to find the different type of heartbeats and group them together as they contain meaningful information. And so one thing we really wanted to focus in this project is the incorporation of domain knowledge. So domain knowledge of the expert, leveraging this domain knowledge to find the patterns the expert or the operator is interested in. For example, let's say a machine produces 10 batches of a product, and the operator knows, okay, the machine has today produced 10 batches. Then it only makes sense to actually look for patterns that occur 10 times in the time series. Then there's a lot of other domain knowledge we can leverage like this. So what did I do within this context? So we developed at KULeuven, developed a novel toolbox called Locomotive. And our toolbox is kind of able to do things that other toolboxes are not able to do. So, for example, it can find variable length motifs. So existing toolboxes require the length of your pattern to be specified. But sometimes this pattern is just unknown to the domain, this length, is unknown to the domain expert. Or sometimes you just have two patterns in your time series with different lengths. So if your method or your toolbox requires the length to be specified, you will not find both patterns. Another thing that our toolbox uses or can use is time warping. And this basically means that you allow some stretching or compression in time of your pattern. So this can really improve the flexibility of the method, and it can really improve the results the results of your toolbox. Then we also support multivariate time series. A lot of toolboxes are still only applicable to univariate time series, so one dimension. And yeah, it has been said multiple times before or talked about multiple times before in this presentation, multivariate time series just occur everywhere in industry. So this work has been published and will be presented at the European Conference of Machine Learning, and also the toolbox source code is available on GitHub if you're interested. So this is here on this slide I show an example of in what kind of use cases our toolbox can be used. So we have a monitored server here, or the data of a monitored server that I show here. So we show the memory usage and the total processor load. And you can all see a very clear pattern appearing in this
in this time series. And this pattern actually occurs with a backup being made of your server. And using our method, we can exactly find where this backup occurs without actually knowing the shape of the pattern beforehand. So we can learn the pattern and find its occurrences. And this is useful also to detect contextual anomalies. For example, we can learn using the time segments. We can learn like the expected time between two backups. Then we can, for example, predict when the next backup is going to happen. And if it doesn't happen at that point, we can throw an anomaly because we expect it to happen, but it did not. And as some of you may know, if you don't back up your data, you may lose it forever. So this kind of thing should be detected when it happens. So another use case, which is kind of related to this, or related to motive discovery, is the bonded interfaces use case. So here we have a pool of monitored network elements, and we measure at each network or network interface is more accurate maybe. So and each network interface we measure the bit rate, so the incoming data traffic basically. And here the goal is to find the network interfaces that are bonded. What are bonded network interfaces? Interfaces where the bit rates behave the same or similarly, where they have when they have the same pattern occurring at the same time. And this actually results from a load balancing process. Like if you have a load balancer, it will split the data, the incoming data traffic over two network interfaces, and so you expect it to behave similarly over time. So in this use case, the goal was to first to detect which network interfaces are bonded, but then also, so here I show two bonded interfaces, but then also where they stop being bonded, so where they start to show dissimilar behavior. And here, I show it in these three red segments, and I zoom in on them here at the bottom, and you can clearly see that in these segments the time series are not behaving similarly at all. So there must be something going wrong in this load balancing process. And then another use case I focused on together with Skyline was the multivariate time series. So when you have multivariate time series, you can look for anomalies. You can take two perspectives basically. You can look for anomalies in the time dimension, so to anomalous time segments, which kind of relates to the Discord discovery. But you can also look at the other dimensions. So are my dimensions, or is a dimension behaving anomalously with respect to the others? And so this brought us to this use case. So the motivation for this use case is when operating normally, relationships between variables or parameters measured at machines holds. And then here I want to give the temperature and fan speed example, but Dennis also kind to already give that for me. But maybe just to repeat, so if your temperature increases, then you also expect your fan speed to increase. And so what we wanted to do here was to detect the time instance where these relationships are violated. So when your temperature increases, but your fan doesn't activate at all. So this can lead to overheating, etc. So we want to detect this. And so what we did here, we took quite a simple approach. So we learn we first learn in a first phase the relationships between the variables or the parameters based on historical data using machine learning models. And then at deployment time, to detect anomalies, we predict the values of the parameters, so the values we expect. And if our predictions are off, this means that there is something unexpected happening. So this indicates an anomaly. And so this example at the bottom kind of is an example of real data provided by Skyline. So in this example, the normal operation is defined as this time series at the top being equal to or approximately equal to the sum of these time series at the bottom. And so here you can see that the time series at the top has a sudden drop, while at the bottom they just stay constant. So this clearly tells us that something anomalous is happening or something is wrong. Okay, so that was my work within the Conscious project. Now I'll give the word to Dan again.
Okay. So again, interrupting very shortly 2 slides. So I'm going to talk about motiflets. So it's actually another algorithm to discover motifs, similar to locomotive. Here's an example. You have this time series, and you have this distinct motif in the middle, I would say, with 4 occurrences. But then we have an existing method called motiflets, and that discovers only one motif of size 7, and it's shown here. And you can see that it's, finds the 4 peaks, but also some other subsequences. So that's an issue. So my work is motiflets++. It's an extension of that. So I started with motiflets, and the motiflets is defined as, in some sense, the best possible motif set. So you can have k occurrences, a pattern that repeats k times, and then you want to find, of all the possible patterns that repeat k times, you want to find the one with the lowest pairwise distance, and that's the motiflet. So I thought that was an excellent definition, and I contacted the original authors with my comments and extensions and so on. And the nice thing, if you email to scientists and say I found a lot of mistakes, they're quite enthusiastic to work with you. So he's been working with me now to find the top M motiflets, and we fixed some mistakes in earlier work. So this is the output of the new methods. So in this case, we discovered 5 motif sets. The first motif sets is also more clean in this toy example, and that's what we did. So it's submitted to a conference, international conference on data mining. So we'll see if it gets accepted. And so, compared to locomotives, stomp and motiflets, we have some different properties. All methods find motif sets. We focus on the top M discovery, and the reason to discover top M is that sometimes the first and second motif are kind of well known from the domain. Like in an electrocardiogram, often the top one motif can be found by different methods, and it's harder to find other interesting patterns that are maybe not that obvious. So that's our focus. It has some advantages. The parameters are easy to select. So, for instance, the length of the sequence is often a parameter. We can just learn it from the data. M is the number of patterns or motifs you want to find. So that's also easy to select. And another advantage is, because we find motiflets, which are the optimal motif sets of a certain size k, that's also an advantage, which results in high quality motifs. Okay, so if you want to try it out, the source code is online. In Python, it's just 2 lines of code, and then you can run it on your time series. Okay. I think this is okay. Okay. So to conclude this session, what I want to show is how we can use the motive sets from Locomotive, from MotiveLets++, for time series semantic segmentation. And the goal of time series semantic segmentation is, given the time series data, try to find the time intervals that have something meaningful, semantically meaningful in the application domain. Or if we reformulate it, time series semantic segmentation performs automatic, unsupervised context detection. Now, to illustrate this idea, I show here a simple time series. This trend data shows how often mail is Googled during a week. And what you can see clearly is that during the working week, people Google their mail more often, specifically around 9 a.m. in the morning when they start working. And in the weekend, they don't Google their mails. So we can actually identify 3 different contexts in this case. Each bar represents a context. And the first context, so where the color is active, that corresponds to the nights in the week. The second context corresponds to the working hours, and the third context corresponds to the weekend. Now, specifically what we do is we learn the context or the probability over the different contexts, which is shown in the middle. And what you can see here is every vertical slice, there is a probability of belonging to each context. For example, in the beginning, the red bar is high, which means Monday morning, still a weekend feeling. But as the day continues, you start in the working hours. And this is different to state-of-the-art, who tries to identify a discrete point, specific point where there is a transition. For example, Friday afternoon, 5 p.m., the weekend starts. It's not always so easy to say at this point there is a transition. Oftentimes it's quite fuzzy. And with a probability distribution, you can actually model this fuzziness, so the probability of one context decreases, while the probability of another context increases. Now, another advantage is that we can automatically model reoccurring behavior, because the probability of contact is high, then it decreases over time, and then it is high again. So these are 2 advantages. Now, how we do this is with PATS, pattern-based time series segmentation, which we've developed at KULeuven also together with Len. And I'm going to give a very high overview. If you want some more information, you can always come to me. What we first do is we learn the common patterns, so that can be motives, or in this case we use discrete patterns, in the time series data, and we search where those patterns occur. For example, the first pattern occurs on Monday till Friday. The second pattern occurs only on a Saturday and Sunday. And then the occurrences of these patterns actually form a embedding matrix. So a matrix saying where the patterns occur, at which locations, which we can then feed to machine learning models to, in the next phase, learn the semantic segmentation or the probabilities over the semantic segments. And this works quite well. On the left side, you can see the time series data that I've shown before. Also on the bottom is the embedding matrix with the black values, or the black pixels representing a higher value, the white value, pixels representing zeros. On the right side, what we did is, this is a publicly available data set for the that measures the blood pressure of a person laying on a tilt table. And here we can also see some nice results. Now I also want to show this result because it also works on multivariate time series. State-of-the-art typically does not bother so much with multivariate data, but we've already heard today that it is quite important to handle multivariate data. So we can also do this. And what I also want to show is that we have made a demonstrator of PATS. Dan has also made a demonstrator of Locomotive. And we'll put them out there next to one of the screens so you can try them out. So definitely come talk to us and you will be able to play around with the parameters and see what the algorithms do. Now, because we now can find this context, we can actually enable context-aware anomaly detection. And to illustrate this, I use an electrical motor. So just on a very high level, an electrical motor, what you do is you apply some electrical energy, you apply a voltage level to the motor. And because of that, the motor will start rotating and out comes mechanical energy. Now this is quite crucial in many industrial applications. So detecting if something goes wrong with an electrical motor is also crucial. In this motor you can measure a lot of different variables, for example the state of flux, as I've shown here. What you can already see there are actually different contexts. So first of all, in the first part and the last part,
I applied a certain voltage level to the motor. In the middle part, I applied an other different voltage level, so different voltage levels, or we can also say different context. What you can also see is that there are strange behaviors in the trend data, namely slightly larger values, and that's because I applied a shift in the rotor eccentricity, which means that the rotor is slightly offset from the center of the stator on the outside. So those kinds of things are not very nice, so you want to detect them so that nothing goes wrong with your motor. And because we now have this context available, we can apply context-aware anomaly detection. And this is a similar data set as I just shown before. The only difference is this one is 20 seconds, the previous one was 2 seconds. But the idea is identical. There are two contexts, and what you can first try to do is just ignore the context, see what happens. And these are the anomaly scores, so the higher the bar is, the more anomalous your sample is considered. As you can see here, on this side, the entire second context is considered anomalous, which is not as desirable. However, if we do take these contexts into account, if we detect anomalies within one context, we get these anomaly scores. And now the two anomalies are correctly identified, and this context is no longer anomalous as we would like to. Now, this is already, I think, quite nice results. However, we want to have a more thorough understanding of how well the method performs. So we did a more elaborate study. And in this slide, there is quite a lot of information. So the approach we developed is actually a method above the anomaly detection itself. So we can use different base anomaly detectors inside of it. Each column represents a base anomaly detector. And you can then apply them in a contextual setting or in the just vanilla non-contextual setting. And in this case, we can see actually that in these two rows, oftentimes using context, most of the time actually, using context improves the performance. Not always, but most of the time it does improve. Now what we've also done on this bar here at the bottom, in this row here at the bottom, we actually computed if the performance significantly improves. So if it's not just a something in the data, but if there's effectively a statistical difference. And then we can see also that for almost all the base anomaly detectors, the performance does indeed significantly improve. So here we can then actually see that the context has a significant improvement upon the base anomaly detector.